the behavior of the lead-acid battery under non-standard conditions. And so there are two things we want to look at. We want to look at non-standard conditions with respect to the degree of discharge, which is to say, if your alternator or your generator is not properly delivering voltage to the battery to keep it charged, that battery will discharge. And so we want to look at how that actually affects the voltage. But we also want to link it into the behavior with respect to increasing and decreasing temperatures. And as is always the case, as we learned in this chapter 7, it's the Faraday equation. It's the opening statement. And again, whenever you see this Faraday equation, which says that delta G is equal to minus the number of electrons engaged in the overall reaction times the Faraday constant times the cell voltage, it reminds us of two things. One, the remarkable linkage between this idea of Gibbs free energy and the actual voltage put out by a cell, and the fact that a very straightforward, simple equation relates those two incredibly different topics. That's the genius of the Faraday equation. And so we're going to use that repeatedly to look at these non-standard conditions, because we can calculate the cell voltage under non-standard conditions by starting with what we know is the expression for the change in Gibbs free energy under non-standard conditions, which is equal to the change in Gibbs free energy under standard conditions plus RT times the log of Q. And remember, when we worked Q out, that represents the process going from reactants to products, because Q is equal to the activities of the products divided by the activities of the reactants, raised to the proper stoichiometric coefficient. So now we have this ability to substitute delta G into this equation, and that means that we can write out this expression under non-standard conditions in terms of the cell voltage. So I just simply substitute that in. That gives me minus the number of electrons times the Faraday constant times the cell voltage under non-standard conditions is equal to minus N times the Faraday constant times the cell voltage under standard conditions plus RT log Q. And so that provides the foundation, because all I have to do is divide through by minus NF, and I come up with the expression for the cell voltage under non-standard conditions, which is equal to the cell voltage under standard conditions minus RT over NF times the natural log of Q. And this is where we remind ourselves that the remarkable relationship between the cell voltage under non-standard conditions and the cell voltage under standard conditions resides in the fact that this quantity RT over NF is extremely small. Typically, it's on the order of 10 to the minus 3. But more than that, Q measures the conversion of reactants to products. So as we go from reactants to products, Q is increasing, all right, but it's the natural log of Q, and that suppresses the quantitative change. And that results in the behavior of all batteries, where we can plot the cell voltage against the degree of discharge, and there's a little tick at the top because of log Q, and then there's this long flat plateau until we get out almost to the end, 99% of the conversion of reactants to products, and it falls off the edge. But of course, the fact that it falls off the edge means in life you can't start your automobile because the voltage is insufficient to turn the starter motor over to start the gasoline engine. So we have now our relationship between the cell voltage under non-standard conditions, the cell voltage under standard conditions, and this remarkable feature that keeps that cell voltage under non-standard conditions almost equal to the cell voltage under standard conditions until we've essentially discharged the battery.